Hello students, good mornings to all of you. You are most welcome in next video lectures of LNT College online studio. Okay, so thank you. Now I am going to start our next topics, which is basically alkali metals and the chemistry of oxides, peroxides and superoxides, right? So oxygen, which is the most important elements and found in gaseous state in the atmosphere, whose concentration is 21% in the atmosphere, right? So it is actually highly reactive. So the metals or non-metals can react with this oxygen to form oxides, peroxides, and superoxides, and sometimes ozonides also, right? So if you uh, talk about oxygen, so oxygen is nothing but diatomic molecule, and which is paramagnetic in nature, right? So this is your paramagnetic. Paramagnetic means in liquid and in the solid state, oxygen is in blue color. So it has blue color, blue color in liquid state, right? Liquid or solid state. Okay. So, but once it is existed in gaseous states, so it remains in colorless in gaseous state. Colorless in gaseous state. Gaseous state. So it remains colorless in gaseous state. Okay. So it has various allotropes and which is actually categorized as oxide, which carries two negative charge, right? And another one is peroxide, so whose structure is O2, carries two negative charge again, and then this is the superoxides, and it is also diatomic, but it carries only one negative charge. Okay, and this is uh, ozonide, which also carries one negative charge. So these are the negatively charged species of oxygens. So they are all reactive and undergo reactions with metals and non-metals. Okay, so here what type of metals we are basically discussing about alkali metals, as you have previously studies about alkali metals. Suppose we have a alkali metals like that, lithium, right? Lithium, sodium, and potassium, and rubidium, and cesium, and francium. Francium, which is radioactive. So here we are not going to consider uh, francium. So only you are going to consider lithium, sodium, potassium, rubidium, cesium. So this is group 1 metals. So it is actually due to presence of one valence electron in all alkali metals, so they are also highly reactive, right? So all alkali metal, all alkali metal actually have one valence electrons, right? One valence electron, valence electron 1 in the outermost shell. So which can be easily ionized, right? Forming a noble gas configuration. So you can think that, so these elements are highly reactive. So because of the ionization of one outermost electron result in the formation of noble gas configuration. So all alkali metals can oxidize its valence electron and carries positive charge. So it will be changed into ionic states, that is Li plus, Na plus, K plus, and rubidium plus, and cesium plus. Okay. So all these ions actually can react with this oxide ion. So first here we are going to consider oxide ion. So what is the beauty of oxide ion is that, um, suppose this is your O, so this is your O2 minus, right? So it has only 8 valence electrons, right? So 8 8 valence electron, right? So, and this is why it is diamagnetic in nature, diamagnetic in nature. So, and the compounds which form through the reaction of oxide ion, actually they are colorless, na? So actually all compounds are colorless. Okay. So due to presence of two negative charge, so it has a high charge density on the oxygen. So it requires high positive charge density to stabilize the compounds. So once, and what is the cause of formation of oxide ion? When oxygen react with H2O, when oxygen react with H2O, that gives oxide ion, right? Oxide ion. So this oxide ion stabilize metals, okay, in a particular oxidation state. Here lithium, so once in a solid state, react with oxygen gas in the atmosphere, right? So it forms Li2O in a solid phase. So this is called lithium monoxide. What happens actually in this reaction is that lithium in a solid phase undergo oxidation, right? So lithium is converted into, here oxidation takes place, right? And this oxygen is reduced, reduction takes place. Reduction means once lithium react with oxygen, so they form lithium monoxides in a solid phase. In this reaction, lithium undergo oxidation through the release of one valence electron, and oxygen molecule gets reduced as oxide ion. So this is what we call it as lithium oxide in a solid state. In another fashion, so it can be prepared through the reaction of alkali metals in liquid ammonia, right? And through bubbling of air from the atmosphere, we can get lithium monoxide, and sodium peroxide and potassium superoxide are oxides depending on the concentration of the oxygen, right? So similar to the lithium, next metal, that is sodium, Na solid, also react with oxygen gas, and they form Na2O, so that is in solid state, that is sodium monoxide, and plus there is also a chance of formation of Na2O2, that is also in solid state. Okay, and similar to potassium, okay, potassium in solid state will react with oxygen in gaseous phase. So then also it forms K2O in solid state and plus sometimes KO2, right? So in case of lithium metal, so lithium monoxide is the major product, but once sodium react with oxygen molecule, then there is a two products, that is sodium monoxide and sodium peroxide. So in this case, this product, that is sodium peroxide, is stable, and potassium react with oxygen gas, result in the formation of potassium monoxide and potassium superoxides. So in this case, potassium superoxide oxide is most stable product, right? So what is the chemistry behind that? Ki different types of alkali metal will form different type of oxides in spite of formation of oxide. They form superoxides, they form oxides, they form ozonides, depending on the concentration of oxygen or air in the reaction media. Okay, so suppose all metal forms like lithium 2, lithium solid, right, plus O2 in liquid ammonia, right? So this forms Li2O. Li2O in the solid state, right? So here solid phase and gaseous phase react with oxygen gas, then result into formation of lithium oxide in the solid phase. And similar to sodium, sodium in solid state react with oxygen in presence of liquid ammonia. They form Na2O in the solid state, right? And potassium similarly K2O in the solid state, and rubidium similarly Rb2O, and cesium Cs2O. So all alkali metals actually form monoxide, but stability depends on the size of alkali metal cations, and this is the trend. Li plus is smaller than Na plus, and then K plus, and then Rb plus, and then Cs plus. Size increases from lithium to cesium plus, right? So the oxide ion, which has ionic radius 126 picometer, okay, and it lithium cation has 0.76 angstrom, or you can say 76 picometer, right? 76 picometer, and it has 172 picometer size. It means lithium cation is smallest in size, whereas cesium cation is largest in size in the respective group 1 of the periodic table, right? So, and oxide ion has 126 picometers, means cations are smaller than anions. Okay, so a small cation will polarize larger cations effectively. According to Fajan's rule, lithium plus, okay, so lithium plus, which has high charge density, means charge per volume ratio is very high in case of lithium plus cation. Okay, and because of the localized charge density on lithium cation, so it has high tendency to attract oxide ion, and because oxide ion has two negative charge. Okay, so more negative charge requires more positive metal, because once you move from lithium cation to cesium cation, or from lithium sodium, potassium, rubidium, cesium, and francium, electropositive character increases. So all alkali metal cations are electropositive in nature because of presence of +1 oxidation state. So this oxide anion, whose size is greater than compared to Li plus, so they will stabilize two lithium cation. Okay, Li plus, 2 lithium plus, and then O2 minus. Because oxide ion has high negative charge density, so it can accommodate two lithium cation, result in formation of LiO bond, right? So O bond, and a metal oxygen bond, and this actually uh, forms Li2O. It means in this ion, structure, total number of, that is nu, is equal to 2 molecule 2 mole lithium plus 1 mole oxygen, that is 3 ions in a unit formula, right? So once you decides the formation of monoxide of alkali metals, then the number of ions in a unit formula is 3, right? Total number of ions present in the monoxide is 3. Okay, and what actually, you know that Kapuscinski equation actually gives us idea about the lattice enthalpy or stability of the oxide compounds in case of monoxides. So actually delta HL, right? HL inverse is directly proportional to number of ions and product of charges on cation and anions, and it is also inversely proportional to the interionic distance. Okay, so in case of monoxides formation, nu is equal to 3, and total charges Z plus is equal to +1, and Z minus is equal to -2. It means -1 multiply, it means delta H L is proportional to total number of ions 3 and mod of Z plus and mod of Z minus, that products give 2. It means delta HL 6 upon R plus R minus, right? So 6 times, actually greater the charge density and greater the number of ions, more lattice enthalpy will be obtained, right? So because of a small size of lithium cation, so they will be stabilized by oxide anions. Okay, but once you move from lithium monoxide to cesium monoxides, the stability decreases because of the larger cations, and you know that larger cation actually prefer to stabilize larger anions. Okay, so cesium plus actually is the largest cation in the group first alkali metals. So it will uh, destabilize oxide ions because it has very large size. So 172 picometers, and here oxide ion has 126 picometer. So it will uh, not able to stabilize oxide ions. Okay, so the stability decreases. Okay, stability decreases. Stability decreases. So in this family, lithium monoxide is the most stable monoxide, and cesium monoxide is the least stable monoxide, right? And is most stable, right? So because of the polarization effect of lithium cation, so it polarizes oxide ion and formation of the metal oxygen bond. But this cesium cation does not stabilize oxide ion, so because of the large size of the cesium cation, and in the lattice structure or in the lattice vicinity, cations anide does not exist. So such type of compounds actually do not found in the uh, chemistry. So the monoxide formation actually decreases in the group. So monoxides, all alkali monoxides are basic in nature, like Li2O solids or Na2O solids. Okay, so these alkali metal oxides are actually basic in nature because once they react with H2O, okay, so result in the formation of hydroxide, so that is LiOH, okay, LiOH, and this is your NaOH, 2NaOH, 2LiOH. So that is actually base. So once monoxide, they react with H2O to form hydroxide. So that is why they are all basic in nature. Okay. So what why actually lithium are stable in monoxides, and why sodium do not stable in case of monoxide formations? So because of the uh, size and lattice effect and lattice enthalpy. Size and lattice enthalpy, these are the two factors actually determines the stability of any metal oxides or uh, another type of oxides. So these are the chemistry of the alkali metal monoxides. So they are all basic in natures. Okay. So next, we can move towards peroxides. As you know that, so once oxide anion react with more oxygen, that is O2, half O2 in gaseous state, they form O2 minus, right? So this is your superoxide. So here two oxygen atom total carries two negative charge. Okay, so total number of electron in this species, actually valence electrons if you are talking, then 6 14 electron, right? In the valence state there is 14 electrons, so all electrons are supposed to be paired, so that is why they are diamagnetic na, this is diamagnetic, right? And the compounds are colorless. Okay, so the structure of this super oxide, uh, like that, O and O. This is the structure, and overall 2 negative charge, right? So this is peroxide ion. This is what we call peroxide ion, right? So this is peroxide ion. It means 2 negative charge, so they will be equally distributed to on each and every oxygen atom. So O minus 1, and then this is minus 1, right? So here 2 oxygen atom each carries minus 1 positive, minus 1 negative charge. So you can say that in this structure, each oxygen has each oxygen has minus 2 oxidation state, right? Each oxygen has minus 1 oxidation state, right? Whereas in case of monooxides, oxygen has minus 2 oxidation state. So oxidation state decreases, right? So what is the beauty of this peroxide structure? So due to low charge on oxygen atom, so it will not able to uh, attract lithium cation strongly, and because of oxide ion is smaller than this super this peroxide ion, right? So peroxide ion is larger than the oxide anion. So it means this peroxide ion will be stabilized by large cations, but due to this minus 1 charge on oxygen, they will attract sodium. Suppose that this is your sodium cation, right? So sodium has low charge density compared to lithium plus, so it will create low positive field. Okay, so it will not attract um, this actually oxide ion. So rather it attracts peroxide, which has more oxygen as compared to oxide anion. So it will uh, react with oxygen, then Na2O2 in solid state it forms, right? So those sodium cation here is stabilized by one peroxide anion. It means 2 Na plus and O2 2 minus, right? In the crystal lattice, 2 sodium plus and 1 oxide anions. So total number of ions in a unit formula again, that is 3. That is 3. Nu is equal to 3. And in case of charge, Z plus is also plus 1, and Z negative is minus 2. So again product of charges is 2 multiply 1 2, and number of ions is 3. So in case of oxides and peroxide, number of ions and product of charges are same, right? So in this case, actually uh, this peroxide anion can stabilize sodium cation through the formation of ionic bond, right? So suppose uh, lithium lithium in a solid state, it will react with O2 in gaseous state in the presence of liquid ammonia, then Li2O. But sodium Na2O2 it forms, right? And potassium K2O2 in spite of KO2 also forms, right? And इसी तरह से similarly rubidium R2O2, and in case of cesium, cesium 2O2, right? So plus Li2O2. This is not found in nature. So because peroxide ion does not stabilize small and highly charged cations in the lattice. So that is why this uh, oxide does not exist in the nature. But once we move from lithium onwards, sodium plus has large size, so it will comparatively stabilize peroxide ion. So the most stable peroxide is the sodium peroxide, right? So it does not form sodium oxide as a stable product, right? So similarly, potassium peroxide, rubidium peroxide, and cesium peroxide so forms, but stability depends on its lattice structure, its size, and its stabilization effect. Okay, so what actually happens is that once this form peroxides, sodium peroxides, in case of sodium peroxide, so that is Na2O2 in solid state, right? So once it is heated, then it forms delta Na2O Na2O plus oxygen gas, right? Na2O plus O2 gas. So once sodium peroxide is heated, result in the formation of sodium monoxide and oxygen gas that is liberated in the reaction. Okay. So similarly, K2O2 in solid state, once it is heated, K2O plus oxygen gas, and in case of rubidium, Rb2O2 in solid state, if it is heated, then it forms Rb2O plus O2 gas. Yeah, you can say this is half, and this is also half, and this is also half. So what is the probability of formation of monoxide of other alkali metal peroxides? So lithium does not form lithium peroxide, so there is no question of the formation of the uh, or decomposition of the lithium peroxide. So on from lithium onwards, sodium peroxide, once it is heated, they form sodium um, oxides, that is monoxide, potassium monoxide, and rubidium monoxide. What is the probability of this uh, monoxides formation, right? So this can be rationalized with the help of thermochemical ionic data and by using the Kapustensky equation. So uh, lattice enthalpy of the product and of the reactants. So lattice enthalpy different, delta HL difference is equal to delta HL M2O, right, minus delta HL M2O2, right? So if this difference is high, it means the product is stable. If this difference is high, then monoxide is stable in the product side. Then monoxide monoxide is stable in the product side, right? And if this difference is low, very, very low, it means the peroxide are not able to be decomposed to form monoxides. So the in the next page, we have actually elaborated that Na2O2 solid state, so that will be thermally decomposed to Na2O plus half O2 gas, right? So in case of this, and in case of monoxides, actually lattice enthalpy, here we have taken the data, right? So in case of sodium monoxide, delta HL is equal to 2702 kilojoule per mole, kilojoule per mole, right? In case of sodium peroxide, it has 2260 kilojoule per mole, right? And what is the difference of these two value? The difference delta H difference L is equal to 442 442 kilojoule per mole, right? But once we move from sodium onwards, suppose potassium like rubidium, in case of rubidium to O2 in solid state, so once it is heat is to thermal decomposition takes place by the formation of rubidium monoxide plus of oxygen gas, right? So what is the lattice enthalpy actually in this case? So delta HL in case of rubidium peroxide, what is the data that I have extracted actually? So in case of rubidium, actually 1980 kilojoule per mole, or in case of rubidium monoxide 2316. And what is the difference of lattice enthalpy? So that is actually 336 kilojoule per mole, right? So what this data actually indicates that once the alkali metal forms peroxides, right? And what is the probability of stability of this peroxides? That can be elucidated through the help of these data. These data are basically lattice enthalpy, which is determined through the thermochemical ionic data by the Kapustensky equation, right? So in case of sodium peroxide, this is the difference for 42 kilojoule per mole. It means there is high difference. And in the downtrends, rubidium peroxides forms rubidium monoxides, and the difference in lattice enthalpy only 336 kilojoule per mole, right? In case of 440. So what it indicates actually is that means this product is favorable, means the sodium peroxide thermodynamically it will undergo into decomposition to form sodium monoxide, whereas potassium peroxide or rubidium peroxide or cesium peroxide does not undergo to thermal decomposition at normal temperatures to form monooxides, because the stability of this monooxide is low, because here lattice enthalpy difference is low. It means there is a less chance to exist in the lattice. So it will does not forms effectively. And similarly in the cesium cesium peroxide in solid state, once it is heated, so it can form cesium 2O plus half oxygen gas, it will be released, right? So there is little chance to form this cesium monoxide, because here lattice enthalpy will be again very low, very low. So if difference in lattice enthalpy is very low, it means the product side is not much more stable. So what inferences it can be drawn here is that once we move from top to bottom, means sodium peroxide to potassium peroxide to rubidium peroxide and then cesium peroxide, the thermal decomposition is difficult. It means formation of monooxide decreases. It means all peroxides, so that is formed through the alkali metals, does not form monooxides, rather it forms peroxides. So this is the elaboration of existence of monooxides uh, and peroxides, right? So next we can elaborate that the temperature increases. It means thermal decomposition requires high temperature, okay, and then only it can be decomposed into monooxides. And it is also due to the size effect, larger cations will effectively stabilize peroxide ion, and it will not easily broken down into monooxides because of low thermal and lattice enthalpy difference. So you can say that the monooxide formation in the downtrends decreases in the respective group 1 metals. So sometimes this oxide anion it forms peroxide anion, right? So this will take another oxygen from the atmosphere, it will be converted into 2O2 minus, right? So this is added in the system, right? So one oxygen molecule is added to the peroxide to form 2 mole superoxides. It means superoxide that is O2 minus, so it has only 13 valence electron, right? So it has only 13 valence electrons, right? So one electron remain unpaired. Again, one electron remain unpaired, right? So due to presence of one unpaired p electron, so it is again paramagnetic in nature. So, and due to presence of one unpaired electron, so it so electronic transition, and the compound which forms by alkali metals, they are actually colored. So colored compounds forms, colored compounds, right? So this superoxide, actually, it has, you can say that it is called free radicals. So free radicals, right? So one electron is in anti-bonding molecular orbitals. So number of electron, if it exists in anti-bonding molecular orbital, so it has high reactivity, right? So it has high reactivity, okay, and it also possesses most, yeah, powerful oxidizing agent, oxidizing agent, right? So superoxide ion is the most powerful oxidizing agent because of presence of one free electrons. Oxidizing agent means it is highly susceptible to be reduced, right, through the acceptance of one uh, extra electrons, so that it will remain in the paired state, right? So this is the beauty of this superoxide. And what is the structure of this superoxide ion is that, then this is O and this is your O, right? So overall it carries one negative charge, okay? So this OO bond actually exists overall minus one negative charge. So what actually the oxidation state carries oxygen atom like O minus O overall 1 minus means O bond O minus half and minus half, right? So the equally distributed charge. So the oxidation state of oxygen in superoxide is equal to minus half, right? Whereas in case of oxide, oxidation state minus 2. In case of superoxide, oxidation state minus 1, right? M2O2. In case of peroxide, oxidation state minus 1. In case of monoxide, oxidation state. So the oxidation state changes as the different oxide structure forms. So high charge density on oxide anions, and then charge density minus 1, and there is minus half charge on oxide anions. So this oxygen has less repulsion as comparison to peroxide structure, where minus 1 charge exists on each oxygen atom. So it means the size of this oxide anion is lesser than compared to peroxide ion, and then it has superoxide structure. So superoxide anion is largest in size as comparison to oxide anions, right? So here oxygen undergo repulsion. Oxygen means minus 1 charge, minus 1 undergo repulsion, so it will easily try to form oxide anions. So that is why the size of this peroxide anion is smaller than that of superoxide ions, where minus half charge less repulsion will takes place. And in case of what you think about the bond order, so in case of oxygen O2, the bond order is 2. It means O double bond O, right? So in case of uh, peroxide, so in case of peroxide, bond order is equal to 1, right? And in case of superoxide, actually, bond order plus 1.5. It means in case of superoxide, there is more closeness between oxygen oxygen. Oxygen atom remain in more intact, more close to each other because of high bond order. Whereas in case of peroxide, actually, the bond order is 1. It means there is uh, repulsion. It means they do not wish to remain in close to each other. So that is why you can say that this is smaller compared to superoxide anion. So all these oxides and alkali metals superoxides are colored in nature. Suppose lithium superoxide. So what is the reaction of superoxide is that so once lithium in solid state react with oxygen, right? In case in the presence of liquid ammonia, right? So lithium O2, right? So that is lithium superoxide. It forms, right? Excess may. So this is excess amount in gaseous phase. So similarly, sodium forms Na2 NaO2, right? So NaO2 in solid state, and potassium KO2 in solid state, and rubidium in solid state it forms RbO2 in solid state, okay, and similarly cesium in solid state it forms cesium superoxides in solid state, right? So lithium O2, right? So all these compounds are colored. So this is your red in color, and this is your red, brown, and this is your dark red, and this is your orange. This is orange red, orange red, right? So all these super oxide compounds are colored in nature. And what is the lattice enthalpy? What you expect? Here, in case of superoxide, actually, smaller lithium cation uh, will stabilize superoxide ions, but um, does not stabilize superoxide ions, because the superoxide ions are always greater than that of oxide anion or peroxide anions. So, due to high charge density on lithium cation, it will not stabilize this superoxide ions. And similarly, sodium monoxides, right? Sodium superoxides are not much more stable because of the size effect and electropositive characters. But uh, sodium onwards, like potassium rubidium, and cesium, potassium superoxides, rubidium superoxides, cesium superoxides, they are most stable superoxides, right? Like KO2, Rb2O2, Rb Rb RbO2, and then CsO2. So these are the most stable superoxides of alkali metal. Superoxides of alkali metals. Okay. So all these superoxides are basic in nature. So, okay. So they are basic in nature. So because once they react with water, they form hydroxides. So which clearly indicates that so all superoxides are basic in nature. So once you move from lithium to cesium, the formation of normal oxide first increases and then decreases, and secondly the formation of peroxide increases and then decreases, and lastly the formation of superoxide increases. So in case of alkali metal family, normal oxides, which is basically found by lithium, and peroxides, so that is lithium Li2O, and in case of peroxide Na2O2, and in case of superoxide, that is KO2. So oxides, and this is peroxide, and this is superoxides. Okay, so is I think so they are stable compounds in alkali metal chemistry, right? So lattice enthalpy, actually, what do you expect? Lattice enthalpy in case of these oxides. So lithium Li2O, Na2O2, and KO2. Total ions here is 3, and total number of ions in unit formula, that is 3. And in case of superoxides, there is nu is equal to 2. Here only 2 ions present in the superoxide structure, whereas in the peroxide there is 3 ions. So what you expect lattice enthalpy? So lattice enthalpy delta HL in case of peroxide, right, is very high as comparison to lattice enthalpy of superoxide. So because of the number of ions in a unit structure formula. Okay. So if lattice enthalpy is very high, it means that the compounds are more stable, and superoxides are also stable, but they are highly reactive because of low lattice enthalpy compared to peroxide. So it has low lattice enthalpy, right? So what is the beauty and of this superoxide? Here K plus and O2 minus. It means it means Z plus is equal to plus 1 and Z minus is equal to minus 1. So the product of charges Z plus Z minus is equal to 1 and nu is equal to 2. So the lattice enthalpy is 1 by third of the peroxides. So delta HL superoxides is equal to 1 by third of lattice enthalpy of peroxide, right? So, and because of the large size superoxide anion, which is stabilized by larger cations like potassium plus, rubidium plus, and cesium plus. So they have large cationic radius. So it will prefer to stabilize large superoxide anions. So all these cations will stabilize O2 minus, right? So in this way, uh, in the downside of the group first alkali metals, so potassium, rubidium, and cesium form superoxides. Okay, thank you, friends, for listening the chemistry of oxides, peroxides, and superoxides. Okay,